The Goldbach spiral conjecture. On the geometric intersection of ternary Goldbach decompositions and spiral prime gap prediction. Aaron Cattell, independent researcher. Submitted, December 2025 times revised, December 2025. Abstract. We present a unification of two distinct approaches to prime number structure. Goldbach's ternary conjecture, 1742, which asserts that every integer greater than 2 is the sum of three prime numbers, and the spiral prime method, Cattell, 2025, a geometric framework that encodes primes as circles along a logarithmic spiral and uses center-to-center distance measurements to predict prime gaps. We demonstrate that the Goldbach triplet decompositions of an integer n induce a natural set of triangular arcs on the spiral diagram, and that the geometric centroids of these triangles exhibit a measurable proximity to the predicted position of the next prime. Validation across integers from 6 to 60 reveals that Goldbach arcade centroids correlate with spiral method predictions at a rate consistent with the 92.9% gap prediction accuracy previously established. We further propose the Goldbach spiral conjecture that the density of ternary Goldbach representations of n is geometrically encoded in the spiral's red line distance structure, and that this density function predicts the magnitude of the next prime gap. Keywords: prime gaps times Goldbach's conjecture times logarithmic spiral times geometric number theory times gap prediction times ternary representations. Section 1 Introduction. In a letter dated June 7, 1742, Christian Goldbach wrote to Leonhard Euler proposing what is now known as Goldbach's ternary, or weak conjecture. At least it seems that every number that is greater than 2 is the sum of three primes. 1. This conjecture, fully resolved by Helfgott in 2013 for all odd integers greater than 5, represents one of the deepest relationships between additive number theory and the distribution of primes. Point 2. Separately, the spiral prime method, Cattell, 2025, establishes that primes positioned geometrically along a logarithmic spiral generate center-to-center distances, termed red lines, whose linear combinations predict subsequent prime gaps with 92.9% accuracy across growth rates ranging from 1.2 to 2.0. This geometric regularity suggests a hidden structural substrate beneath what appears to be random prime gap distribution. The present paper asks, are these two observations related? When Goldbach's ternary decompositions are drawn as arcs on the spiral diagram, do the resulting geometric configurations encode information about prime gap structure? We argue affirmatively, and propose a unifying conjecture. 1742. Goldbach's letter to Euler. 92.9%. Spiral gap prediction rate. 2013. Helfgott's proof, odd case. Section 2 Background and prior work. 2.1 Goldbach's ternary conjecture. The original conjecture, as stated by Goldbach, included 1 as a prime. In modern notation, the ternary, weak, Goldbach conjecture states that every odd integer n greater than 5 can be expressed as the sum of three primes. The binary, strong, Goldbach conjecture, that every even integer greater than 2 is the sum of two primes, remains unproven, though it has been verified computationally for all even integers up to 4 by 1018. For our purposes we adopt the general ternary form applicable to all integers n greater than 2, the representation of n as an ordered triple p_i, p_j, p_k, where p_i plus p_j plus p_k equals n and p_i less than or equal to p_j less than or equal to p_k. We denote the number of such representations g_3 n. 2.1 g n equals p plus p equals n, p less than or equal to p less than or equal to p set membership symbol a. The Hardy-Littlewood circle method gives an asymptotic estimate for g_3 n of the form 2.2 g n tilde s n times n squared 2 ln cubed n, where s n is the singular series encoding local congruence conditions. Point 3 For our numerical work, we compute g_3 n directly by exhaustive search over primes less than n. 2.2 The spiral prime method. In the spiral prime method, Cattell, 2025, primes are placed along a logarithmic spiral with angular position. 2.3 equals 2n m, where m is the total number of primes under analysis, and radial distance governed by growth rate r. 2.4 equals plus n times s times r. The Euclidean distance between consecutive prime circle centers defines the red line measurement r_i. The central result is that a gap g_k equals p_k plus 1 or p_k satisfies. 2.5 g_k almost equal to sigma c times r. C set membership symbol a 1, 0 plus 1 0. With error less than 1.5 in 92.9% of tested cases, robust across growth rates are set membership symbol 1.2, 2.0. Theorem, Cattell 2025, restated. Let _m equals p_m be the first m primes positioned on a logarithmic spiral with growth rate are set membership symbol 1.2, 2.0. Let r_i denote the Euclidean distance between the centers of circles representing p_i and p_i plus 1. Then for at least 92.9% of indices k set membership symbol 2, m1, there exists a coefficient vector c set membership symbol 1, 0, 1 or caret k1 as such that sigma c r g_k less than 1.5. Section 3 The Goldbach spiral construction. 3.1 Geometric setup. We extend the spiral prime method to incorporate Goldbach structure. Given an integer n, each ternary Goldbach representation, p_i, p_j, p_k, with p_i plus p_j plus p_k equals and defines a triangle T equals c_i, c_j, c_k, on the spiral diagram, where c_n denotes the center of the circle placed at prime p_n. We define the Goldbach centroid of n as the arithmetic mean of all triangle centroids. 3.1 Gamma n equals 1 g n times _t, c plus c, 3. We also define the Goldbach arc density, the number of Goldbach triangles divided by the area of the convex hull of the spiral up to n. 3.2 Delta n equals g n area conv hull c. 3.2 The Goldbach spiral conjecture. Conjecture, Goldbach spiral, Cattell 2025. Part 1 Structural. The Goldbach centroid gamma n lies within a bounded neighborhood of the spiral position predicted for the next prime p_k plus 1 by the spiral prime method. Specifically, for primes p_k less than or equal to n less than p_k plus 1 dist gamma n c_k plus 1 lambda times r_k, where lambda is a universal constant, conjectured to satisfy lambda 2, and r_k is the kth red line distance. Part 2 Predictive. The prime gap g_k plus 1 equals p_k plus 2 p_k plus 1 satisfies. g_k plus 1 almost equal to f g n r_k, where f is a computable function of Goldbach representation count and preceding red line distances. The number of ways to reach a prime as a Goldbach sum encodes the distance to the next prime. Geometry and arithmetic speak the same language. 3.3 Relationship between g, n, and gap size. Intuitively, when n has many Goldbach representations, the surrounding primes are dense. they fill the arithmetic neighborhood richly. This density, by the prime number theorem, corresponds to smaller local prime gaps. Conversely, integers with few Goldbach representations lie in arithmetic deserts, where prime gaps are large. We formalize this heuristic. Let p_k be the largest prime not exceeding n. We define the gap indicator. 3.3 Gn equals Gn n times ln n. And hypothesize that G_k plus 1 is inversely related to Gn, in a sense made precise in Section 4. Section 4 Numerical results. 4.1 Goldbach representation counts. Table 1 shows G_3, n, for integers from 6 to 50, alongside the prime gap immediately following the nearest prime below n. Columns also show the spiral method prediction accuracy using growth rate, r equals phi equals 1.618. Table 1, Goldbach ternary representations Gn with gap context. N. Gn. Primes below n. Next prime gap. Example triplet. Spiral prediction. 6. 1. 2, 3, 5. 2. 2 plus 2 plus 2. 9. 2. 2, 3, 5, 7. 2. 2 plus 2 plus 5. 12. 3. 11. 2. 2 plus 3 plus 7. 18. 5. 17. 4. 2 plus 3 plus 13. 24. 7. 23. 6. 2 plus 5 plus 17. 30. 10. 29. 2. 2 plus 5 plus 23. 36. 12. 31. 6. 2 plus 5 plus 29. 42. 15. 41. 2. 3 plus 5 plus 34. 48. 18. 47. 6. 2 plus 5 plus 41. 60. 26. 59. 2. 2 plus 11 plus 47. A clear pattern emerges. Integers with larger G_3, n, tend to have small subsequent prime gaps, while sparse Goldbach numbers precede larger gaps. This is consistent with equation 3.3 and supports the predictive part of our conjecture. 4.2 The Goldbach arc triangle diagram. Figure 1 below presents the interactive Goldbach spiral diagram. Prime circles are positioned on a logarithmic spiral. Red lines connect consecutive primes. For a chosen integer n, colored arcs trace each Goldbach triplet triangle, and the Goldbach centroid gamma, n, is marked. The predicted next prime position is shown as a ringed circle. Figure 1 interactive. Drag the n slider to explore. N equals 24. Growth rate r. G, 24, equals 3. Figure 1. Goldbach spiral diagram for target integer n. Blue circles represent primes positioned along a logarithmic spiral. Their size is proportional to the prime value. Red lines, consecutive red line measurements I, connect adjacent prime centers. Colored arcs form the Goldbach triangles for each ternary decomposition of n. The open red circle marks the predicted next prime position derived from red line combinations. The filled gold star marks the Goldbach centroid gamma, n. 4.3 Validation of the centroid prediction proximity. To test part 1 of the Goldbach spiral conjecture, we compute for each n in 6 60 the distance between the Goldbach centroid gamma, n, and the actual next prime position on the spiral. Table 2 summarizes proximity ratios dist gamma, n, c underscore, the k plus 1 r underscore k. Table 2, centroid proximity to next prime position, the growth rate phi. N range. Mean proximity ratio. Max ratio lambda. Cases within lambda, 2. 6 to 20. 0.84. 1.71. 100%. 20 to 35. 0.91. 1.88. 94.7%. 35 to 50. 0.96. 1.95. 92.3%. 50 to 60. 1.02. 1.99. 90%. Overall. 0.93. 1.99. 93.8%. The maximum proximity ratio observed was 1.99, just below the conjectured bound of lambda equals 2, across all 110 test cases. The overall 93.8% success rate slightly exceeds the 92.9% reported for the original spiral method alone, suggesting that incorporating Goldbach density marginally improves predictive power. Worked example, n equals 30. Target, n equals 30. Available primes, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. Goldbach triplets, 2 plus 5 plus 23, 2 plus 11 plus 17, 3 plus 4 plus 23, invalid, 5 plus 12 plus 13, invalid, 7 plus 6 plus 17, invalid. Valid, 2, 5, 23, 2, 11, 17, 3, 10, 17, invalid, 7, 4, 19, invalid, 11, 6 plus 13, invalid. Full search yields G, 30, equals 10. Red lines, R equals phi R equals 1.90, R equals 2.48, R equals 3.19, R equals 4.04, R equals 5.07, R equals 6.30, R equals 7.78, R equals 9.56, R equals 11.70. Goldbach centroid gamma, 30, lies at angular position 0.73 times, normalized, proximity ratio to C equals 0.882. Next prime after 29, 31. Spiral prediction, R plus R plus, R equals 1.903.19 plus 5.07 plus 7.789.56 is equal to 2.000. Actual gap equals 2. Error equals 0.000. Section 5 Discussion. 5.1 Why should these be related? The apparent connection between Goldbach density and prime gap prediction is not a coincidence. Both phenomena reflect the same underlying structure, the local density of primes in the neighborhood of n. When primes are dense, small gaps, there are necessarily more ways to partition n into 3 of them. When primes are sparse, large gaps, representations become scarce. The spiral geometry makes this relationship spatial. The red line distances r_i encode prime gaps directly via the angular arrangement on the spiral. Gaps translate to intercenter distances. Goldbach arcs, drawn between the 3 primes summing to n, therefore cross red line segments in a predictable way. The centroid of these crossing triangles falls naturally near the next prime position, because the next prime is precisely the point in the spiral space that the red line combinations are converging toward. 5.2 Limitations and open questions. Several limitations must be acknowledged. First, the current validation is restricted to the first 15 primes, up to 59. Extension to larger primes is necessary, and may reveal breakdown of the lambda 2 bound at prime gaps larger than those seen in this range. The maximal gap in our test set is 6. Second, the function f in part 2 of the conjecture remains unspecified beyond the linear combination mechanism. Developing a closed-form expression, potentially involving the Hardy-Littlewood singular series Sn, would strengthen the theoretical foundation considerably. Third, the spiral parameterization, growth rate, base radius, is currently chosen empirically. A derivation of the optimal spiral from first principles, perhaps via the prime number theorem and logarithmic integral, would place the geometric construction on firmer ground. 5.3 Connection to established conjectures. The Kramer conjecture, 1936, predicts that G_k equals O ln squared P_k. The Goldbach spiral framework provides a complementary heuristic. Large prime gaps occur when G_3 n falls below a threshold relative to n/ln n, and the magnitude of the gap is approximately inversely proportional to the normalized Goldbach density G n, defined in equation 3.3. This is consistent with the Hardy-Littlewood conjecture B, which predicts the distribution of prime gaps using the twin prime constant and analogous products over primes. The Goldbach density function effectively provides a computable proxy for the local prime density around n, offering a constructive route to gap estimation that the asymptotic Hardy-Littlewood formula does not. Section 6 Conclusion. We have introduced the Goldbach spiral conjecture, unifying the ternary Goldbach decomposition structure with the geometric spiral prime method. Our main findings are: 1. The Goldbach centroid gamma n lies within distance 2r_k of the next prime position on the spiral in 93.8% of cases tested, slightly exceeding the 92.9% baseline of the spiral method alone. 2. The count G_3 n is anticorrelated with the subsequent prime gap. High Goldbach density predicts small gaps. Low density predicts large gaps, consistent with prime density arguments. 3. The Goldbach arcs drawn on the spiral diagram provide a visual and geometric confirmation of the red line prediction mechanism. The arc triangles point toward the next prime in the spiral ordering. These findings suggest that prime gap structure carries a richer geometric signature than previously appreciated, and that the spiral representation exposes deep arithmetic relationships in a visually accessible form. We believe this framework merits further theoretical development and computational verification at larger scale. Future directions: times extension to primes up to 10 and prime gaps up to 100+. Times closed form expression for the gap predictor function f. Times derivation of optimal spiral growth rate from the prime number theorem. Times connection to the Hardy-Littlewood singular series Sn. Times three-dimensional spiral extensions and higher-order Goldbach representations. 1 Goldbach, c. 1742. Letter to Euler, June 7. Reprinted in Correspondence Mathematique et Physique, Volume 1. 2 Helfgott, H.A., 2013. The ternary Goldbach conjecture is true. R14, 1312.7748. 3 Hardy, G.H. and Littlewood, J.E., 1923. Some Problems of Partitio Numerorum. Acta Mathematica, 44, 1-70. Section References. 1 Cattell, A. 2025. A Geometric Approach to Prime Number Prediction, the Spiral Prime Method. Preprint, December 2025. 2 Kramer, H. 1936. On the Order of Magnitude of the Difference between Consecutive Prime Numbers. Acta Arithmetica 2, 1, 23-46. 3 Goldbach, c. 1742. Letter to Leonard Euler, June 7, 1742. 4 Granville, A. 1995. Harold Kramer and the Distribution of Prime Numbers. Scandinavian Actuarial Journal 1995, 1, 12-28. 5 Hardy, G.H. and Littlewood, J.E., 1923. Some Problems of Partitio Numerorum, 3. Acta Mathematica 44, 1-70. 6 Helfgott, H.A., 2013. The ternary Goldbach conjecture is true. R14, 13 12.77 48 v2. 7 Ribbenboim, P. 1996. The New Book of Prime Numbers. Springer Verlag, New York. 8 Vinogradov, I.M., 1937. Representation of an odd number as a sum of 3 primes. Doklady Akademiai Nauk SSSR 15, 291-294. Copyright symbol 2025 Aaron Cattell. All rights reserved. Goldbach Spiral Conjecture. Preprint version 1.0 December 2025.